All right, welcome back to Ecology. So the last thing we did was that little bit on introgression that was part of this larger discussion of birth of species and death of species. Right now I want to do a little bit on species diversity. And a little bit more with scaling. Of course, we did a little bit with species diversity when we talked about scaling spatially as alpha, beta, and gamma diversity. Now what I want to talk a little bit about is scaling as it relates to the factors that we think influence species diversity. There are a number of factors that ecologists talk about that we believe have this effect on species diversity. And keep in mind, just as I've been saying all along, species diversity can be measured as richness, it can be measured as abundance, or it can be measured as a combination of those two. Usually when people say diversity, they're talking about abundance and richness together. But again, once we start dealing with larger spatial scales and larger time scales, this diversity measure really is richness. Okay? All right, so the first thing ecologists noticed was that if you go out with a particular sized quadrat, you get a number of species that's determined as richness. And then you set out a slightly larger quadrat, quantify richness, and you keep increasing the size of the quadrat each time. One way to do this efficiently is with what's called a nested quadrat, where you have one large quadrat and then you quantify different areas within that larger quadrat. So this is more of what's called a nested design. One of the first things people noticed was if you take these values, right, area that you're measuring over and richness or diversity on the y-axis, trying to figure out what happened to my other marker since this one is kind of losing its ink here. One of the things they noticed was that this relationship tends to be exponential. That as you look at larger areas, richness increases exponentially, and that's what's shown here. So if we think of richness as S, if you recall when we were doing island biogeography, we used S as number of species, and then S hat was the equilibrium number of species. And then area we'll keep as A, right? Then we can look at this relationship as a very simple equation here, where the number of species is equal to some coefficient C multiplied by the area raised to some value Z. More on Z in a second. But these two are basically just numbers that are used to fit the data. It's really the y and the x variable that are being plotted, and then these two values arise from the curve that best fits that data. Those of you from lab know the trick of taking an exponential and log transforming it to a line, and that's what we're going to go ahead and do here. So if we log transform this equation, we would get the log of S equal to the log of the coefficient C plus, bring this down in front, Z times the log of A. And that would give us our linear equation, which is shown here. log of A, and that's log of S. Okay. Now this Z value has taken on some ecological significance, in part because of MacArthur and Wilson and their island biogeography hypothesis. Here's area and number of species. These are log transformed axes, which is why things go linear instead of exponential. And they describe Z as a measure of isolation. So higher Z values equals more isolation. That is, you can get these different species area relationships for different locations, and if the slope of this line, right, if the slope of that line is higher, that means we're looking at more isolation, a greater distance away from the mainland, a greater distance away from the source of colonists. Okay? All right, so this is a very fundamental relationship. The more area you look at, the more species you tend to find. It seems kind of simplistic, but ecologists are at their very nature very simplistic scientists. The next thing that is important in determining species diversity or species richness are some things that we've already talked about. We already came up with a few hypotheses, believe it or not, for why there are so many species in different areas. But now we're getting away from kind of species area, right, to scaling up of area as an explainer of species richness. So let's just look at some stuff that we've already looked about. The first hypothesis would be the disturbance hypothesis. This is the intermediate disturbance hypothesis. We have some measure of a disturbance here, some measure of number of species here as richness, and that there's some intermediate level of disturbance which gives you more species diversity. At low disturbance levels, competition becomes important. Certain species outcompete other species, and we have loss of species due to this importance of competition. At high levels of disturbance, competition is not important, but being able to withstand the disturbance is important, but there are only a few species that can tolerate this high level of disturbance. And therefore, at some intermediate level, competition isn't that important, and neither is the disturbance. And this combined level of low competition, low disturbance gives you high species diversity. Now, there's good empirical evidence for this particular hypothesis. This could work. So good empirical evidence for this, and it's been implemented by ecologists who are very applied. So, for example, prairies. Right, you have the prairies out, starting like in Iowa, Illinois, Minnesota, etc. These grasslands. They were used to being exposed to periodic fire. One of the things humans do is try to prevent fires, so they stop fires. And by stopping this fire disturbance, you move the prairies to a low disturbance situation, and as part of that, lost a lot of species. Currently, these prairies are managed where every year somebody goes out and does what's called a prescribed burn. They burn the prairie, and in doing so, establish a little bit of disturbance periodically, And this little bit of disturbance helps to maintain more species in the community. Okay. Number 2. This is a Keystone consumer hypothesis. In the Keystone consumer hypothesis, there's a particular species in the community that is a keystone. So keystones, when you're looking at kind of old buildings, what they would do is take archways out of stone, and then they would lean the 2 piles of stones toward each other, and then they would put in this little keystone. And this keystone is what holds up the arch. If you remove the keystone, I really wish I knew what happened to my other marker. Normally I blame it on my kids, but I don't think they'd want a marker. They don't have anything to do with it. So you have this keystone, you remove the keystone and the archway collapses. So a keystone species is a species that, because it's in the community, you have all these other species that can remain within the community. We did a little bit on the sea star piesaster. Because it eats blue mussels, it prevents blue mussels from out-competing all of the other species within the intertidal zone. The sea star is acting as a keystone predator. It removes the competitive dominant and therefore allows other species to exist within the community. If we remove the sea star, our community would turn into a monoculture of blue mussel. Okay. Another example, on the island of Mauritius, you have these beautiful beaches. Mauritius is in the Atlantic Ocean, close to the Caribbean. And the problem is lots and lots of seagrass everywhere. So what the hotels on the beach did was they went out and they removed all of this seagrass, because people don't like to swim in seagrass, right? If it hits against their legs, it feels slimy. So they removed all this seagrass, and when they did that, they removed all these species that live in amongst these seagrass meadows, all the flora and fauna that live on the seagrasses, that rely on the detritus from the seagrasses, all the way down from bacteria all the way up to sea turtles, were gone, because that seagrass is a keystone species in this community. It is the reason why that community exists. What they very quickly found, the hotels very quickly found, was the removal of the seagrass meant that water flow increased, and you got these very turbid habitats, lots of sand kind of distributed within the water column, and their beautiful beaches with nice clear water turned into beautiful beaches with really turbid water that nobody wanted to swim in. Okay? All right, number 3, the one we're going to spend a little bit more time on, is the latitudinal diversity hypothesis. Latitudinal diversity hypothesis. Let's start out with just some basic observational data here. Number of species of breeding bird species, trees, and mammals just in North America. And the further up you go in latitude, the fewer of each of these species. The closer you get to the equator, the more species you get. There seems to be a relationship between the latitude and the number of species that we see. Here's mammals, just looking at continental North America. And again, low number of mammal species, an increase in the number of mammal species as we move toward the equator. Okay? This nice kind of latitudinal diversity gradient that we see. And then we have some explanations for why we might be able to observe such a diversity gradient. Because it turns out there's a lot of argument as to why you get more species as you move toward the equator. Okay? All right, the first hypothesis for the latitudinal diversity gradient is a productivity hypothesis. So let's just talk a little bit about productivity. Productivity is basically a measure of light energy being converted into carbon-carbon bond energy. So it should be somehow related to photosynthesis, right? We've got photons from the sun being converted to carbon-carbon bonds through photosynthesis. Productivity is a measure of the amount of this carbon-carbon bond material that's being produced. It's a biomass measure. It's the amount of light being converted into a certain amount of biomass. Okay? The thinking is there should be a tremendous amount of productivity at the equator relative to these higher latitudes away from the equator, simply because there's more light at the equator. And if there's more light at the equator, that should correspond to more carbon-carbon bonds being produced. That is, more light means more carbon-carbon bond production, which means more biomass production. More biomass of plants, this would be what we would call the primary production. And then from there, we've got our first level consumer, and then our second level consumer, et cetera, all the way through that trophic web that we've talked about before. The idea is if you had more material to start with, it might make it possible to have more different species existing at these higher trophic levels, right? In North America, we might have